Understanding and mastering the EVM is a huge part of going from a beginner slash intermediate blockchain developer or security auditor to becoming a really fully fledged advanced blockchain engineer or security researcher. And so that is exactly what we're going to do today. We're going to lay out a complete guide to the EVM, everything you need to know, the structure of the EVM, how it actually ends up working out when we call a function, and even some very sneaky gas optimization tips along the way. So if you're looking for an easy to understand guide on mastering the EVM, then you're in the right place. All right, but of course, first of all, why should you listen to what I have to say about the EVM? Well, my name is Owen, and about 2 years ago, I started building a protocol in the Ethereum space, and in the process of that, actually realized that the security space had a huge issue. And so out of that, I founded Guardian Audits. And ever since then, we've uncovered dozens and dozens of critical and high vulnerabilities and audited well over 100 smart contracts and spent personally over 1,000 hours doing it. And so my goal with all of the videos that I put out, and especially this one, is to distill down everything that I've learned along the way so that ultimately you can become a much better blockchain engineer or security researcher. All right, with all that out of the way, let's dive right into a complete guide of the EVM. All right, great. So in this guide, we're going to cover all the different types of areas where data can be stored in the EVM. And then once we get an idea of the high level layout of all of these different areas in the EVM, then we're going to dive in and see how these areas can actually be utilized during a transaction execution, and how the EVM actually works with each of them. All right, so let's get started. First of all, there are actually 6 different places where data can be stored. And this is, of course, most commonly the stack, memory, call data, and storage. But also, you can store things in code, obviously, that is at any particular address. And then also logs, which is a write-only way to emit events and log stuff. So in this guide, we're really going to drill down and focus on the first 4 here. We're going to get a very solid understanding of the stack, memory, call data, and storage. Okay, so first of all, let's dive into the stack. Now, I'm sure many of you watching this video are already well aware of what a stack is and exactly how it functions, but for those of you who don't, a stack is a very simple data structure where you can just take items. Let's say I have this item here, and I can push it onto the stack. Let's say this is my stack. It's just a little cup here. So then we put that item into the stack. There it goes. It's in the stack now. So this item's now in the stack. And then what we can do is we push another item. So we take another item and we push that item now onto the stack. And so now this item comes here, we grab it, and now this item goes onto the stack. And then what we can do is we can pop from the stack. And when you pop, it comes from the top. So the thing that I just put on when we pop from the stack comes off, right? And that's what we get. And then I can pop again, and I can grab this thing and pop that off afterwards. So what are these things that we're pushing in and popping off in the stack for the stack in the EVM? So in the stack for the EVM, we store 32-byte words and we push them on and pop them off. So when I store something on the stack, it will be a hex 32-byte thing, right? So if I wanted to store the number 1, then I would have a bunch of zeros here. And then literally the very last hex character here would be 1. And then all of these, this would be 32 bytes. And remember, each of these 2 pairs of characters here makes up a single byte, right? So if we break this off, then we have 4 different spots. We have 0, 0, 0, 0, and this gives us the first character of 0 in our hex, and then we have 0, 0, 0, 1, and this gives us the second character in our hex of 1. And so that's our byte. And in this first word, the entire value for this first word is 1. So if I want to push 1 onto the stack, I take this 32-byte word and I push it onto the stack. And then you can push other words on top of that and pop those off. And of course, there are also functions to swap these around. So oftentimes you'll have different, so let's say you have multiple words. Let's say this is all on the stack. Here's a word, here's a word, here's a word. You have OX and then a bunch of zeros, right? So you have all these words. Now, often what will happen is the first 1 or 2 items, the top 2 items on the stack, will be used for interacting with a lot of opcodes, and we'll dig into exactly what opcodes are in just a minute. And of course, the types of things that are stored onto the stack and pushed on and popped off and used to interact with opcodes like this are uints, bools, addresses, or even pointers to areas in memory and areas in storage, which we'll get into right now. Now, memory is somewhat similar to the stack in that it also functions based off of 32-byte words, but it doesn't use any sort of pushing on and popping off. Instead, you can write to specific memory words and choose exactly the bits that you want to write to. And so memory is used to store, of course, structs, and it's even used internally by Solidity behind the scenes. So because memory is used in this special way, it actually has a very particular layout. So when we're talking about memory words, then we have, of course, OX00, which is the first position for a word in memory. And then, of course, you have all of the 32 bytes from there until you end up with OX20. And you'll remember that if we go to a Python shell here and we go and type in OX, we could just put 20 here and 16, then we'll get 32, right? So this is the hex value, OX20 converted to a decimal. So this is at a 32-byte offset from OX00 is the next memory spot. And both of these memory spots here, 00 and OX20, all the way up to OX40, everything here, all of the zeros stored here, so you have a bunch of zeros here, and that goes on, and you have 32 bytes here, there's 32 there, and then of course you have the same thing here. Both of these words from OX00 and OX20 are reserved for Solidity to have some scratch space to work around with when doing things like hashing functions and things like this. And then at OX40, this word is the first word that's not reserved as scratch space, but it is actually very special in that it is home to the free memory pointer. And this word will initially be OX80. So what is the free memory pointer and why does it point to OX80? Well, the free memory pointer points to the first spot in memory, the first word that doesn't already have something written to it or isn't reserved for some other reason. And so this is so that if we ever want to write something to memory, you can read the free memory pointer and then immediately know where it is safe to write something new to memory without overwriting something old. And so the follow-up question is, of course, why does it point to OX80 when, of course, the very next word is OX60? So OX60 is also going to be completely empty with just a bunch of zeros. But this word is actually intended to be empty always. This is used for the initial value for dynamic arrays as just a 0 value. So of course, this word in memory should never be written to, and that's why the free memory pointer skips over it and points to OX80. And so at 0x80, it's going to be initially completely clean. Nothing will be stored here, and it is actually safe to write new stuff to be stored in memory here. And it's actually interesting to note that 0x40 is the free memory pointer, and it comes before 0x60, because when initializing this memory to 0x40, that means we only have to load in so many words before it and sort of allocate those as memory. And so this way, if a transaction never wrote memory beyond this 0x40, then we actually wouldn't have to sort of load in another memory word here. And so this is a very slight optimization where if they were to be flipped, then you would always have to be loading in another empty spot when we initially write to the free memory pointer in a new transaction, which we'll see in a minute. And to make what I'm saying here really clear, if I go and I write to memory and I do what is called an mstore opcode, which we'll see in a second, and I say I want to write to some slot that is, like some really big number. I want to write to some really huge number down here. This is going to be extremely expensive due to memory expansion, right? So if I'm writing to this, then we now all of a sudden have to keep track of all of these memory words below it. And so as your memory expands like this, the gas costs are actually going to exponentially increase. All right, and the next is, of course, call data. So call data also stores arbitrary bytes, but the difference here is that in call data, you can only read from this area. You cannot write anything to call data. And for this reason, it is much cheaper to be reading things and accessing things from call data. And so, of course, if you can help it, then always err on the side of simply reading things from call data and avoid copying things from call data into memory whenever possible. So if you never need to modify something that is call data, then always just read it from call data and do not copy it into memory. And of course, if you have a memory parameter for one of your functions, but you never need to modify that memory parameter, then use it as call data. Okay, and then finally we have storage. Now, storage is the most expensive of all of these different areas where you can store data, but it is also the only one of these areas that is permanent. All of these other areas like the stack, memory, and call data, they all go away. They're all temporary places to store data during a transaction. So in this sense, storage is almost like the blockchain database that you can think about. And it works in somewhat of a similar way to memory, where we have 32-byte words that get stored in storage. Except this time we have storage slots, and there are no reserved areas for Solidity or no like free memory pointer or anything like this. And so essentially, if we think about the blockchain state and how we have, all these different accounts, like let's say we have account here, an account here, an account here, an account here, then for example, if we go to this account here, then this account has a nonce associated with it. It has a certain amount of ether, so it has native tokens. And then of course it might have some code associated with that address. Of course, if this is home to a contract, and then if it's home to a contract, then it is also likely to have some storage. And now storage also breaks down into these slots. So we have all these different keys for storage, and each of these keys is essentially a uint 256, a 256-bit number, or something that occupies a full word, whereas the keys for the state of the blockchain in each of these accounts is of course a 160-bit number or address, right? And then both of these, of course, the state of the blockchain with all of these different accounts, and then of course the tree here for different storage slots are Patricia Merkle tries. And we're not going to get into exactly this video, but this is essentially how the storage is ultimately laid out as a persistent piece of the blockchain state. So of course, how do all these different areas of the EVM actually come together to give us what we know as Ethereum? So what brings it all together and makes all of these things interact with each other and really workable is this idea of opcodes. So we're on the Ethereum yellow paper here, and we have all of the opcodes pulled up. And we can see that essentially what an opcode is a specific instruction to give to the EVM in order to do something. So imagine you had a little robot and you gave him 4 different spots to just put stuff. And then you just gave him stuff, you just handed him random crap and then told him instructions on what to do with it, where to put it. That's essentially what the EVM is. So we can see we have something like the add opcode, which literally just takes 2 items that are on the stack, like we talked about, and adds them together. And then, of course, stores the result of that addition into the first spot on the stack. And you can see along the side here that for each opcode, we have a corresponding hex code here. And this will play into how exactly these opcodes are able to be translated into something that can be actually executed by the EVM. But first, before we get into that, let's examine a few opcodes that interact with the areas of storage and memory and the stack that we just looked at. So here we can see we have a number of push opcodes which correspond to pushing things onto the stack. So here we can see we have a push 1 opcode, and it goes to push 2, and it goes all the way up to push 32. And each of these correspond to pushing a n byte sized thing onto the stack. And remember, it goes up to 32 here because 32 bytes is of course a full word, and full 32 byte words are what is stored on the stack. And so if I only push 1, then the other 31 bytes are essentially padded out with zeros, and then you get that 1 single byte on the end. That thing is pushed onto the stack. And then of course here we have OX50, which is the pop opcode, which removes an item from the top of the stack. And right below that we can see imstore and imload. And so these opcodes are useful for storing things in memory. Right, imstore will take the actual position, and so imstore will save an entire word into memory, and it will take the first 2 things on the stack and use those as the value to be stored, and then also the position at which it should be stored. And then of course imload is doing the opposite. We are reading something from memory, right? So we're giving a location in memory to read, and then we are getting that value and putting it onto the stack. And then you'll notice we even have a imstore 8 opcode here, which saves a single byte to memory. And then right below that, we can see the sload and store opcodes, which do a very, very similar thing just for storage, right? So I can store and load things at a particular storage slot. So there are many, many opcodes, and I encourage you to go read the Ethereum yellow paper and actually see all of them for yourself, get familiar with all of them. But now it's time to see how these opcodes come into play and are actually used by the EVM. So we'll remember that if we go to our Ethereum yellow paper here, we can see these opcodes correspond to these hex values here, these single bytes. And we'll actually be able to see this if we go into Chisel. Here we have literally just a example contract set up here. And what we can do is we can get address this.code, and here we have individual byte codes for opcodes, right? So some of these hex characters here are opcodes. And so we can see if I add a variable here, we can add a uint I, and we can say it equals to the type uint256.max. Now if we go ahead and look at our contract, we've added this single declaration of I, which is the max value of the uint256, and then now we can have a look at address this.code. And you can actually see here that we've gotten a good amount of extra Fs here that we didn't have before, right? We had this 73 FFFFF here. This is this set of f's, but we didn't have this big statement of f's here. So if we actually count this out, the number of bytes here for this set of f's is actually 32 bytes of f's. And this is the value for our I variable here. This is the uint 256 max, right? So uint 256, of course, has 32 bytes, and each of the bits inside of all of those bytes are 1, and so we have f for every single byte. We have ff. And so before all of these 32 bytes of f's, we can see we have this 7f byte right here. So if we go and find the opcode that corresponds to 7f, we'll see what exactly is happening with this big set of f's here. So here we are at the 7f opcode, and this is the push 32 opcode. So we're pushing a 32 byte word onto the stack. And this perfectly makes sense, right? So we're taking this big 32 bytes of f's and we are pushing it onto the stack. That's exactly what this statement here is doing. Now, there's actually a wonderful website for distilling things down and actually getting to look at the bare opcodes themselves, and that is EVM Codes. So we can see we have a basic sort of default contract here for a counter already set up for us, and we can run the count method and we can see exactly all of the different opcodes that it's going to run through, and you can even step through all of them and see how the memory, the stack, storage is manipulated throughout the transaction. But what we can do is we can actually walk through and see, okay, what is the EVM doing at the opcode level as we're reading this bytecode here and executing the call data, and then we can see how the transaction will function. So here we can see I've called the count function, and we can see a few things happening off the bat here. So I can see a push 1 opcode of 80, and then so we're placing 80 onto the stack. So that's our first 32 byte word on the stack, is literally just a bunch of zeros, zeros, and then in the literally the very last byte, that byte corresponds to 80. So we have OX80 on the stack, and then we push another word, and this one is OX40. And then what we do with those two things on the stack is we store them. And so what we're doing here is exactly what we talked about just a little bit earlier when we were talking about this free memory pointer. So this is exactly what we're doing. We're taking OX80 and we are storing it at OX40. And so this is at the beginning of any transaction that happens, is we're going to start up by setting that free memory pointer. And then what we're going to do is we're essentially going to have a sequence of opcodes here to check if the call value was non-zero, because of course the function that we called is not payable. So we're going to get the call value, that's going to place that onto the stack at the top. We're going to duplicate it, so now we have two of those. So this will check, is the last thing on the stack 0? If it is, put a 1 there. If it isn't, put a 0. And then we're going to push 2 for this. And so now what we're doing here is we're pushing 2 bytes onto the stack, and we've got this 0, 0, 10, 0 value. So basically OX10 here. That is the most recent word on the stack. And then remember, we have our is0 result after that. And of course, for this transaction, I did not provide any message.value. So this is0 will result in true, which means there will be a 1 there. And then we get to the jump I instruction. And if we go and find jump I in the Ethereum yellow paper, then we can see conditionally alter the program counter, so where the program is, and we'll look at that in just a second. So here the notation might be slightly confusing, but they set the program counter to what is on the 0th of the stack, so whatever is literally on the top of the stack. If that first value, our result of is0, is not equal to 0. So our is0 result was 1, and so it's not equal to 0. And so what we will do in our case is we will actually jump to this program counter of 10 here, And what this will do is it will essentially move us, you'll see, so the program counter here is right here on the side. So once we get to jump I, we're at OB, and then what we'll do is we'll end up jumping to 10 here. And so we can sort of step through that and see that now we're at the jump dest, right? We just jumped to this destination here, and you always have to jump to a jump destination, otherwise the whole program will revert. And then now that we're at the jump destination, we've loaded in, we've put the free memory pointer where it needs to be. We've had that safety check that makes sure that we didn't send ether to a function that isn't supposed to accept it. Now what we do is we clean up the stack a little bit, and then we push on this for value, and then what we do is we get the call data size and put that on top of it. So what the stack looks like right now is we have 4 right here, and then we have the call data size right here. And then what we do is we have this less than opcode. And so the less than opcode will check, is this call data size less than 4? And that means 4 bytes, right? So if call data size is less than 4, then we're going to end up, so less than, I believe it will put a 1 onto the stack if it is indeed less than, which means that we will jump I to 004C if it is less than. And then if we jump to 4C, if we find 4C, then we see that this ultimately leads to another revert case, right? So if we provided some call data that was smaller in size than 4 bytes, meaning that it couldn't possibly even be a function selector, then we need to revert, as that's clearly invalid call data. You're not even attempting to call a specific function. And just really quickly on function selectors, they are essentially the first 4 bytes of the Kechek hash of the function sort of parameters and signature here, and we can actually easily get the function selector if we do a cast sig of, let's say, get, and we can see that this is the function selector for get using the handy foundry cast. And then of course for the function that we called, which is count, we can cast that as well and get count, and then see, okay, here is the function selector for count. So when we supplied call data to call count, we immediately gave this function selector as the first 4 bytes as a part of that call data to specify this is the function that we are calling. So with that in mind, let's step through, let's see this validation of the call data size in action. So we push that on, we check if it's less than, we push stuff on, and we're going to see us not jump. So jump I, and then we're just going to go to 1A. So here we are on 1A, and then what we do is we load the call data, and then you can see we're about to do a shift right, and we're about to shift right by this E0 amount. So it's important to note that call data load is going to load in a single word of call data onto the stack. And then what we're going to do is we're shifting right by this E0 value. So let's find out what E0 corresponds to. We can see E0 here, and we can see that it is 224. So what's the significance of this, of course, is if we have 256 bits in a uint in a word that is 32 bytes, then if we're shifting it to the right, if we're taking a value, shifting it to the right by 224 bits, we end up with 32 bits all the way on the right. And so essentially what we've done here is we've taken the call data, whatever was in that first word of the call data, now we have shifted it all the way to the right until there's just these 32 bytes here, or I'm sorry, 32 bits here, 32 bits. That's literally all we're left here is 32 bits. Instead of having a full word, we've shrunk it down to 32 bits, which is of course 32 divided by 8 bits per byte. We have 4 bytes here, and of course, what is 4 bytes but a function selector? So exactly what we're doing here is we're getting the function selector from the call data onto the stack. And then what we're doing, as you see, we have these push 4s. You might actually recognize some of these selectors, is we're pushing the function selectors in the contract onto the stack, and we're comparing it against this value that we just got from doing this shift from our call data. So we figure out essentially what function am I calling with my call data, and then we say, well, what functions do we have in this contract? And then we check one by one and we see, does this function selector match this, for instance, this function? If it does, then ultimately we're going to push a location that sort of, it maps to where that function begins, where the opcodes that can basically play out the function logic actually live. And if it doesn't, then we're going to continue on and look at the next opcode. So you might recognize this OX666 because we did a sig of count, and that is exactly the function selector for count here. So we are actually on this first attempt going to see that these are equal, and then we're going to push this on, and then we're going to jump to that portion of the opcodes. But before we sort of step this through and actually go there, there's a few things to note. Of course, why is it that this was first? Now, you might be thinking that, oh, well, it's just because count was first here and it had the auto-generated view function, the getter function for count, and since it's first here, those were maybe just put at the top of the contract or something like that. But it's actually because the function selectors here are ordered by numerical value. So for instance, if I take this 0666 here, and if we want to make this into a decimal integer, we can see it's this value. Meanwhile, if I take the very next one and I go and we make this into a decimal here, then we can see it is considerably bigger. And then even more so, if I go to the next one after that, then what we'll see is we have this, and then that one's even much bigger than the one before it. So these are ascending in the numerical value of the bytes for the function selector. And so when we have, I think it's 4 functions or less in a contract, it will actually do a linear search like this where it will go through all of them one by one. And so it will actually be more gas efficient, technically speaking, at this opcode level. Call a function that has a lower byte value for its function signature, because you only have to get to this first one and then you say, oh, well, this is the first one that we're calling. We don't need to waste gas doing all these other opcodes checking for all these other function signatures. We're just going to jump right to where that logic is and then execute it. However, when there are more than 4 different functions here in a contract, then it actually switches to using a binary search, right? Because all of these are actually ordered in order of ascending byte values. Okay, and then we can see that we continue to walk through, and then we push the selector on, we see if it's equal, then we push where the location of all that logic for this function is, for this getter function, and then we're going to jump to it. We're going to jump to 51 here until we will ultimately get to an S load to actually load in that storage slot and then ultimately return it as a part of the return value of the view function. So that is absolutely everything that you need to know about the EVM and how these things actually execute and become executable as bytecode at a low level. I really hope that this video was informative for you. Perhaps the EVM was something entirely mysterious before this. I really hope that this made it very digestible and easy to understand. And for those of you who already had a very in-depth knowledge of the EVM, I hope that this just confirmed your understanding, and then of course maybe you picked up a few little things along the way that you didn't know. So I really appreciate you watching the entire video up to this point. Of course, if you are a protocol developer or you're working on a team and you're getting ready to launch some sick new DeFi application and you're looking for a security audit or beginning to think about that process, then get an absolutely free set of first pass security notes from myself when you go to guardianaudits.com/quote and you fill out an application, and then we will get back to you with some initial first impression security notes of the protocol and of course a quote for a security audit. And of course, if you know any teams who are building something cool and looking for a smart contract audit, send them to guardianaudits.com/quote. And of course, if you're looking for a community to connect with other security-minded individuals, people who are interested in blockchain security and want to really grow out their skill set as security developers and learn from others, connect with others in the space, and even participate in team audits where you get the chance to team up with people from across the world and learn from their methodologies and get rewarded for findings that you come up with as a team, and go check out lab.guardianaudits.com and apply to join our community of growing auditors. All right, that's everything for this time. I can't wait to see you in the next one.